Have you ever marveled at a single drop of water? Perfectly beaded on a waxy leaf, holding its shape almost like magic?
Yeah.
Or maybe you've seen a tiny insect literally walk across a pond surface without any trouble.
Yeah, it's amazing stuff.
Even something like a boat gliding through water seems simple, but there's a surprising secret there too. These everyday things, we kind of take them for granted, but they hide some really fascinating physics.
They absolutely do.
Yeah.
What you're seeing there in those moments are the fundamental properties of fluids in action.
Oh.
Understanding these unseen forces, how liquids and gases behave, from the microscopic dance of molecules right up to the flow of an ocean current, that's really the key to unlocking how our physical world works.
And that's exactly our mission for today's deep dive. We're going to pull back the curtain on these essential properties of fluids. We've gathered all our source materials, and we're ready to sort of extract the most important insights just for you. So, okay, let's unpack this. When we talk about a property in the fluid world, what exactly are we getting at, and why is that distinction important?
Well, fundamentally, a property is just any characteristic we can observe or measure about a fluid system. Things like its temperature, its pressure, volume, mass.
Okay.
But what's really insightful, especially for engineers, is understanding the difference between what we call intensive and extensive properties.
Ah, okay, so what's the big difference there?
Intensive properties,
Yeah.
they don't depend on how much fluid you actually have. Temperature, pressure, density, those are the classic examples.
Right.
If you pour out half a glass of water, the water's still in the pitcher. It's got the same temperature, same pressure, same density. It's inherent to the substance.
Gotcha.
Extensive properties, though, they do depend on the quantity,
Right.
like the total mass or the total volume. Pour out half the water, the total mass changes. Simple as that.
Makes sense.
And often, to make calculations easier, engineers talk about specific properties. That's just an extensive property divided by the mass, like specific volume or specific energy.
Okay, that clarifies things. So we can describe the fluid itself no matter the amount using these intrinsic qualities. And speaking of describing the fluid, I've heard about something called the continuum approximation. Sounds a bit complex.
It sounds complex, but it's actually a remarkably powerful simplification. Imagine just an incredible number of molecules packed into even a tiny speck of oxygen. So many, so dense, that for almost all practical engineering problems, we can treat fluids like water or air, not as individual atoms bouncing around, but as a smooth, continuous substance, sort of like a jelly.
Ah, I see.
And this simplification, it lets engineers solve incredibly complex real-world problems, designing airplane wings, predicting weather without getting bogged down, tracking every single molecule. It's really elegant.
That's a great example of simplifying things. Okay, so with that base, let's dive into some really core characteristics. Density and specific gravity. Density, that's pretty straightforward, right? How much stuff is packed into a given space mass per unit volume?
Exactly. And its reciprocal is specific volume, the volume a unit of mass takes up.
Right.
And what's fascinating about density is how it responds to its environment, temperature and pressure. For gases, density is directly proportional to pressure
Okay.
and inversely proportional to temperature, which makes intuitive sense, right? Squeeze a gas, it gets denser, heat it up, it expands, gets less dense.
Right.
Liquids and solids, though, much, much less responsive to pressure. They're largely incompressible. Take water, you could ramp up the pressure hundreds of times atmospheric, and its density barely changes, maybe 0.5%.
Wow, okay, so really resistant to pressure changes.
Very resistant. Temperature affects liquid density more, but often still pretty subtly compared to gases.
So that's a key takeaway. Gases are squishy, liquids not so much. And then there's specific gravity, SGO. What's that about?
It's just a handy ratio. It's dimensionless. It tells you how dense something is compared to a standard, usually water at a specific temperature, like 4 degrees C. So mercury has an SG of about 13.6. That just means it's 13.6 times denser than water. Gasoline, much lighter, maybe 0.68. It's a quick comparison tool.
A quick check for heaviness. Got it.
And you also mentioned specific weight briefly.
Yeah, that's just the weight to unit volume. Density times gravity, essentially.
Simple enough.
And when we're talking about gases, we almost always turn to the ideal gas equation of state. P equals OORT is the common form.
Ah, yes, the ideal gas law.
Exactly. It's a fantastic tool because it connects a gas's pressure, density, or specific volume, and temperature really effectively. It works remarkably well for many common gases, air, nitrogen, oxygen, especially at lower densities, so lower pressures, higher temperatures.
Okay.
It's the workhorse equation for figuring out gas behavior in tons of applications,
Yeah.
like calculating the mass of air in this room right now.
Right. Okay, now let's shift gears to something maybe more dramatic sounding.
Yeah.
Vapor pressure and cavitation. We all know water boils, right?
That's when it hits its saturation temperature, and the pressure it exerts as vapor matches the surroundings. Vapor pressure is basically that the pressure a substance's vapor exerts when it's in balance with its liquid form at a given temperature. It's like the liquid's internal push to become a gas.
Exactly. And it's really important not to mix up vapor pressure with partial pressure.
Okay, what's the difference?
Partial pressure is the pressure of a vapor when it's just one part of a mixture, like water vapor mixed in the air around us.
Ah, I see.
How fast water evaporates from, say, a lake. And that depends on the difference between the water's own vapor pressure and the partial pressure of water vapor already in the air.
Right.
But the key thing about vapor pressure itself is that it increases a lot with temperature. That inherent push to vaporize gets stronger as things get hotter.
Which is why water boils at 100 degrees C at sea level, but lower up a mountain.
Exactly. Lower atmospheric pressure means the water's vapor pressure matches it at a lower temperature. And in a pressure cooker, higher pressure means a higher boiling point.
Okay, makes sense. Now, you said cavitation. This sounds serious.
It can be very serious. This links directly to vapor pressure.
Yeah.
Imagine a liquid, like water, flowing somewhere. If, for whatever reason, the local pressure inside that flowing liquid suddenly drops below its vapor pressure.
Oh. Well,
I was right. Even for a split second, the liquid can spontaneously boil right there, forming tiny vapor bubbles.
okay.
Those are the cavities. Now, the bubbles themselves aren't the issue initially. The trouble starts when these bubbles flow along into a region where the pressure is higher again.
And then?
They collapse violently. Think of tiny localized implosions happening over and over. These collapses generate incredibly powerful high-pressure shock waves.
Wow.
This is a huge problem in things like pumps, propellers, hydraulic turbines. First, it reduces performance. You get weird vibrations, noise sometimes described as a tumbling gravel sound.
Annoying, but maybe not disastrous.
But the real problem is the physical damage. Those shock waves hammer the surfaces. They can erode metal, cause pitting, lead to fatigue failure, literally chew away impeller blades.
So it can destroy equipment.
Absolutely. It highlights how a seemingly small pressure drop, maybe from a design flaw or just running conditions changing, can lead to really catastrophic failure. It's a hidden danger.
Yikes. Okay, so from those destructive forces, let's maybe broaden out a bit to energy. How do fluids carry and transform energy?
Well, when we talk about the total energy of a fluid, we're really summing up lots of different forms. There's the microscopic stuff tied to the molecules themselves, their motion, the forces between them. We bundle that up as internal energy, usually symbol U.
Okay.
Then there's macroscopic energy the fluid has due to its bulk motion, like kinetic energy, or its position in a gravitational field, potential energy.
Right, velocity and height, basically. And I think I heard you mention thermal energy earlier.
Yeah, often in engineering, when we're talking about the parts of internal energy related to temperature, sensible and latent heat, we just call it thermal energy. It helps avoid confusion with the process of heat transfer. And for fluids that are flowing, engineers use a really handy combined property called enthalpy, symbol H.
Enthalpy. Okay, what's that combine?
It basically packages together the internal energy with something called flow energy or flow work, which is pressure times specific volume, PV. Think of it as the energy needed to both be the fluid and to push it along.
So it simplifies things for moving fluids.
Exactly. It streamlines the energy accounting for systems with flow. We also have specific heats, CP, CV, which tell us how much energy is needed to raise the temperature of a fluid under constant pressure or constant volume conditions. Crucial for heat transfer calculations.
Okay, a lot packed in there. Now let's explore how fluids react to being squeezed or heated. Compressibility and the speed of sound. We know fluids expand when heated or depressurized, contract when cooled or squeezed.
Right, and to quantify how much they resist squeezing, we use the coefficient of compressibility, often called the bulk modulus. Let's call it K. It basically tells you how much pressure change you need for a certain fractional change in volume or density, keeping temperature constant.
So a high K means it's hard to squeeze.
Exactly. A large K means the fluid is very resistant to compression, essentially incompressible, like liquids. We said earlier, water needs huge pressure for a tiny density change. That means its K value is very, very large.
And you mentioned this incompressibility can cause problems. Water hammer.
Yes, precisely because liquids, like water, are so incompressible. Imagine water flowing fast in a pipe and suddenly a valve slams shut. The water stops abruptly, but the water behind it is still moving.
Pile up.
Kinda. It creates an intense, localized high-pressure zone right at the valve. This high pressure then propagates backwards through the pipe as a wave, traveling at the speed of sound in the water.
Ah, pressure wave.
A very strong one. It bounces back and forth, causing the pipes to vibrate, make that characteristic banging or hammering noise. It's not just noise. It can damage pipes, fittings, valves.
So that's why you need things like water hammer arresters?
Exactly. They provide a cushion to absorb that pressure surge.
Interesting. Now, what about gases and compressibility?
For an ideal gas, it's simpler in a way. The coefficient of compressibility, K, is actually just equal to the absolute pressure of the gas.
Oh, really? So K changes with pressure for a gas?
Yes, which means at high pressures, even a tiny fractional change in volume can cause a huge change in pressure for a gas, much more sensitive than liquids.
Okay. And there's another coefficient related to temperature.
Right, the coefficient of volume expansion, usually beta, this measures how much a fluid's density changes with temperature while keeping pressure constant.
And this is behind heat rises.
Precisely. Hotter fluid is generally less dense, so it rises. This drives natural convection, everything from breezes to ocean currents. For an ideal gas, beta is simply the inverse of the absolute temperature, 1T.
It's interesting comparing them. You said heating water makes it noticeably less dense, but compressing it hardly does anything.
Yeah, it shows how differently liquids and gases respond. Gases are far more sensitive to both pressure and temperature changes in terms of their density.
Okay. All this connects to how fast disturbances travel. The speed of sound.
Right. The speed of sound, c, is just the speed at which an infinitesimally small pressure wave travels through the medium.
Like the water hammer wave, but any small pulse.
Exactly. And for an ideal gas, the speed of sound depends only on its temperature, specifically the square root of temperature.
Only temperature, not pressure or density.
For an ideal gas, correct. Temperature is the key. That's why sound travels faster in warm air than cold air.
And the thunderstorm trick. Count the seconds after lightning.
Yeah, sound travels about, what, a kilometer every 3 seconds in air, roughly, so you can estimate the distance.
Cool. And building on speed of sound, we get the Mach number.
Yep, named after Ernst Mach. It's a really fundamental ratio in fluid dynamics, especially for gases. It's simply the actual speed of the fluid or an object moving through it, v, divided by the local speed of sound, Cmam and Vcc.
So Mach 1 is?
Speed of sound. Less than 1 is subsonic, greater than 1 is supersonic. Much greater, maybe 5 or more, is hypersonic. And right around Mach 1 is transonic, which has its own complex physics.
And you mentioned something interesting. An aircraft's Mach number can change even if its speed doesn't.
Right, because the speed of sound c depends on temperature. So if a plane flies into warmer or colder air, even at the same airspeed v, its Mach number, Vc, will change because c changes.
Fascinating. Okay, let's move on to viscosity. This is like the fluid's stickiness, right?
That's a good way to think about it. It's internal resistance to motion, or you could say it's resistance to flowing. Think about pushing your hand through air versus water versus thick honey.
You definitely feel more resistance with honey.
That's viscosity in action. It's directly related to the drag force a fluid exerts on anything moving through it or on adjacent layers of the fluid itself.
So where does this resistance come from, like at the molecular level?
It's different for liquids and gases, which is interesting. In liquids, it's mainly due to the intermolecular cohesive forces the molecules are attracted to each other and resist sliding past one another. Stronger forces mean higher viscosity, like in honey or glycerin.
Okay, and gases?
In gases, those cohesive forces are much weaker. Viscosity there comes more from molecular collisions, momentum exchange between molecules moving at different speeds in adjacent layers.
Collisions causing friction, sort of?
Kind of, yeah. Think of it like this. Faster molecules from one layer collide with slower ones in the next, transferring momentum and creating a resistance to the relative motion.
So how do we quantify this? You mentioned shear stress earlier.
Right. If you imagine fluid flowing in layers, like cards in a deck sliding over each other, the shear stress, tau, is the force per unit area resisting that sliding. For many common fluids, water, air, oil, this stress is directly proportional to how fast the layers are sliding relative to each other, the rate of shear strain, duty.
And the proportionality constant.
That's the dynamic viscosity, usually symbol mu, sometimes called absolute viscosity. It's the measure of that stickiness. Fluids where this relationship is linear are called Newtonian fluids.
And if it's not linear,
Then they're non-Newtonian. Lots of complex fluids are like this: blood, paints, ketchup, toothpaste. Their viscosity can change depending on how fast you try to make them flow.
like toothpaste seems thick but flows easily when squeezed.
Exactly, that shear thinning behavior. Some act like solids until you apply enough force, like Bingham plastics.
Okay. And there's another viscosity term, kinematic.
Yes, kinematic viscosity, usually nu. It's simply the dynamic viscosity divided by the density of Requeo. It often pops up in equations where inertia and gravity effects are important relative to viscous effects.
Got it. Now, the effect of temperature on viscosity. You said this was counterintuitive.
It really is. For liquids, viscosity decreases as temperature goes up.
Like the warm honey example. Flows easier.
Right. The molecules have more thermal energy. They can overcome those cohesive forces more easily, so the resistance to flow drops.
Makes sense. But gases?
Gases do the exact opposite. Viscosity increases with temperature.
Increases.
Because viscosity in gases is due to molecular collisions. Higher temperature means molecules are moving faster and more randomly. This leads to more frequent collisions and more momentum exchange between layers, which translates to greater resistance to flow, higher viscosity.
Wow, that is counterintuitive. Liquid gets thinner when hot, gas gets thicker.
In terms of viscosity, yes, it's a really key difference. And engineers use devices called viscometers, often involving rotating cylinders or plates, to measure these viscosity values accurately.
Okay. Fascinating stuff. Finally, let's talk about the skin of a liquid surface tension and the capillary effect. We started with water drops and insects walking on water.
Yeah.
Why do drops form spheres? How can insects or even a small steel needle float?
That's surface tension at work. Think of it as a force acting along the surface of the liquid, tending to pull the surface molecules together, almost like an elastic membrane stretched over the liquid.
Okay, but why? What causes that force?
It's those intermolecular attractive forces again. A molecule deep inside the liquid is pulled equally in all directions by its neighbors. But a molecule at the surface has neighbors below and beside it, but none above it in the liquid.
Right.
So there's a net inward pull on the surface molecules. This inward force causes the liquid to try and minimize its surface area for a given volume. And the shape with the smallest surface area for a volume is...
sphere.
Exactly. That's why small drops are spherical.
Yeah.
And this skin is strong enough, due to these cohesive forces, to support the weight of very light objects, like insects or that carefully placed needle.
It's literally holding them up.
Balancing their weight, yes. We could even measure surface tension using things like a wire frame dipped in liquid. The force needed to pull the frame out against the surface tension film tells you its strength.
And you mentioned soap. How does that fit in?
Soaps and detergents are surfactants. They significantly reduce the surface tension of water. They get in between the water molecules at the surface and weaken those cohesive forces.
Which is why soapy water cleans better. It can get into fabrics.
Precisely. Lower surface tension allows it to wet surfaces and penetrate small gaps much more effectively.
Okay. Now, curved surfaces. You said there's a pressure difference.
Yes. Across any curved liquid interface, the pressure is always higher on the concave side, the inside of the curve.
Like inside a bubble.
Exactly. For a spherical droplet, the pressure difference is 2 times the surface tension divided by the radius. For a soap bubble, which has 2 surfaces inside and outside, it's twice that. Pelos force SR.
And the pressure is higher for smaller bubbles.
Yes, inversely proportional to the radius. Tiny bubbles have surprisingly high internal pressure.
Okay. And this leads to the capillary effect. What's that?
That's the tendency of a liquid to rise or fall in a narrow tube, a capillary. You see it if you stick a thin glass straw in water. The water level inside the straw creeps up slightly above the water level outside.
And it curves up at the edges. The meniscus.
Right. That happens when the liquid wets the tube material, meaning the adhesive forces, liquid to solid, are stronger than the cohesive forces, liquid to liquid. Water is attracted more to glass than to itself, so it climbs the walls.
And mercury does the opposite, dips down.
Correct. Mercury doesn't wet glass. Its cohesive forces, mercury to mercury, are much stronger than the adhesive forces, mercury to glass. So it pulls away from the glass, causing the level inside the tube to be depressed, lower than outside, with a downward curving meniscus.
So it's a battle between sticking to the walls and sticking to itself.
A perfect way to put it. Cohesion versus adhesion.
And how high does it rise or fall?
The height depends on the surface tension, the contact angle, which measures wetting, the liquid density, gravity G, and the tube radius R. The formula is roughly H equals 2 scos.
So the key thing is it's inversely proportional to the radius.
Exactly. The narrower the tube, smaller r, the higher the capillary rise, or deeper the fall. For water, in a very thin glass tube, say less than a millimeter wide, the rise can be several centimeters.
But for wider tubes?
It becomes negligible pretty quickly. For water, once the tube diameter is more than about a centimeter, you barely notice any capillary effect.
Okay. Now, you mentioned something about this earlier, and it sounded intriguing. Someone proposed a perpetual motion machine based on this.
Ah, yes, the classic capillary PMM idea. Quite clever on the surface.
So the idea was water rises, say, 5 centimeters in a thin tube all by itself, drill a hole just below that 5-centimeter mark,
Let the water spill out due to the free rise,
turn a tiny turbine.
and generate continuous power from nothing. Free energy.
Sounds too good to be true. Why doesn't it work?
Because it violates the first law of thermodynamics. You can't create energy from nothing, especially not from a static equilibrium situation.
Okay, but why doesn't the water spill out? What's the catch?
The catch is the pressure inside that risen water column. It's actually lower than the atmospheric pressure outside the tube.
Lower.
The upward force, due to surface tension, pulling on the meniscus at the top, exactly balances the weight of the raised water column, plus the pressure difference. The system is in equilibrium. The pressure at the 5-centimeter mark inside the tube is atmospheric, but just below that, inside the water column, the pressure starts dropping below atmospheric.
So if you drilled a hole below the 5-centimeter mark,
The pressure inside would be less than the atmospheric pressure outside. Instead of water flowing out, air would actually leak into the tube.
no free energy then. The surface tension force perfectly balances everything out.
Precisely. You can't extract network from a system that's already perfectly balanced and static. A very important lesson in thermodynamics and fluid statics.
So wrapping this all up, what does this mean for you, the listener? We've really gone deep into these fundamental properties of fluids, from just defining them to seeing how density, pressure, temperature interact, to the drama of cavitation, the subtleties of viscosity, and that almost magical surface tension. We've seen how these underpin everything from flight to water drops to why that perpetual motion machine was, well, a pipe dream.
Exactly. And these aren't just abstract concepts for a textbook. They are absolutely critical. They form the backbone of fluid mechanics. If you're designing anything involving fluids, pipelines, pumps, engines, even understanding blood flow,
Right.
you need to grasp these properties. And understanding them helps develop critical thinking. It lets you look at a claim, like the capillary PMM, and analyze why it can or cannot work based on fundamental principles.
We really hope this deep dive has been useful, maybe giving you a shortcut to understanding these key ideas, perhaps with a few surprising facts along the way.
And maybe it sparks some curiosity. We encourage you to think about where else these properties might be showing up in your world. What other everyday fluid phenomena might have some complex physics hiding just beneath the surface?
Definitely something to think about. That's it for this deep dive. Until next time, keep exploring the hidden physics all around you.